This is part 2 of our series circuit presentation from ELCT 205. When we left off, we were talking about single subscript voltage drops in a series circuit, one where a voltage is represented by a single point. We know that voltages are representing the difference of potential between 2 points. So how do we explain single subscript? A single point voltage representation comes from an implied reference, and that implied reference, or second point, of which you are determining the difference between the single point and that point, is always ground. So single subscript is always referencing ground. And so if we go back to part 1, we talked about how any single subscript value of voltage can be converted to a double subscript by subtracting the 2 point values. So in this example, we had a VA value of plus 5 volts, a VB value of plus 3 volts. In order to determine a VAB value, you take the value of VA with its magnitude and polarity of plus 5 volts, and you subtract VB with its magnitude and polarity of plus 3 volts. As a result, your VAB value would be plus 2 volts. Well, when it comes to voltage sources, they can be represented in the same way. A voltage source can be represented as something called a point source, represented by a single point. And because we know that voltages are the difference between 2 points, once again, when a source is represented as a point value, it's always with reference to, or implying with reference to, ground. So even if you don't see ground in a circuit, or even if you don't see ground in the representation of a circuit with point voltages, it's understood that that point and its voltage value is referenced to ground. So let's go to the textbook then, and we'll look at a couple of examples, and I'll explain further here. So here we see an example from the textbook. And let's take a look at the top of this slide. If we look here, here's the circuit that's being simplified by showing a point source. If we look at the source, we can see the negative terminal is grounded. So we've got a negative terminal ground. If we look at the load, we can see the load is also grounded at that same point. Both of those are a common reference point within the circuit. So the circuit could be simplified to show the load connected to the ground and the source as a point source as plus 10 volts. Look at the point right here. If you were to indicate its reference to ground voltage, that would be plus 10 volts. Obviously plus 10 volts over here. So all you're doing is simplifying the circuit to say plus 10 volts with respect to ground is being applied to a load connected to ground. And this is what gives you this circuit representation here. So what would that look like if we were to look at an example such as this? Well, there's a couple of different ways you can approach this when it comes to circuit problem solving. One of them we can remember is that this is essentially a single point value. This E1 is equal to plus 5 volts. So we could call that point A. We could call this E2 as minus 8 volts as point B. Then we could say that VA is equal to plus 5 volts and VB is equal to minus 8 volts. And now, if we wanted to come up with a VAB value, which would represent the total potential difference across a single component, because remember, we essentially want to know what is the V value here to determine current through that device. Well, we need to know the total voltage, and that can easily be done by doing a VA minus VB value to give us our VAB. So VA here would be plus 5 volts minus 8 volts to give you a total of plus 13 volts. So if we wanted to draw that circuit, remember this is indicating that the voltage A is 13 volts positive of B. If we want to redraw that circuit, it could be redrawn as a 13 volt source with point A, point B, and between that is a 52 k ohm resistor, and now your current I just simply becomes 13 volts divided by 52 kilo ohms. Okay, now what's going on here over in this other circuit? Well, remember, you can convert any single point value to a source that's traditionally shown with two terminals by simply understanding that if I have a resistor, which I know on this side is plus 5 volts as a point source, and over here it's minus 8 volts as a point source, we can represent that as a voltage like this with respect to ground, okay, of 5 volts, a voltage like this with respect to ground as a 8 volt value. And if we want to show that as a closed loop, we know we can connect grounds together directly because they're the same point. And now we have a closed loop, and what do we have to do is we have to look at our total motivating force. If we look at our total motivating force in this circuit and we move our way around and count for all voltage sources, we can clearly see that these are series aiding connections for those sources, giving us an E total value of 13 volts. Now all we have to do is know what our R total value is, and in this case we have a single resistance. So it's easy to determine our total value is 52 k ohms. Now your calculation of voltage drop polarities and the direction of current is easy. The motivating force causes current in this direction. The voltage drop polarities are plus and minus, and you have everything you need to solve for that circuit. All right, now we're going to talk about a practical voltage source. Previous to this, all of the voltage sources we've represented in any of our circuit schematics or problem solving are essentially ideal sources. And that is to say they're a source that it doesn't matter how much current that you draw from that source, its voltage will remain the same. So if we take an ideal source of 12 volts, it doesn't matter whether you're drawing 1 amp or 1,000 amps from that 12 volt source, the source will continue to deliver 12 volts. That's called an ideal source. In reality, ideal sources are not, there is no such thing as an ideal source. We often use it for simple circuit analysis. But when it comes to a practical source, it includes something called internal resistance. And in order to relate to that, let's say it's dark and you're looking at a vehicle with its headlights on in the parking lot. And then the person driving the vehicle starts the vehicle. What do you notice about the headlights? They dim while the motor's being cranked over and being started. And that's really because the motor and the cranking of the motor is the highest current load in all of your vehicle, or all of that vehicle. And when we're drawing that kind of current from a practical source, it means that the internal resistance of a practical source comes into play, and the voltage drop of the internal resistance, because of the high current, has to be subtracted from the voltage internal source in order to determine the load voltage. So all practical sources include internal resistance. And therefore it means we can make a statement such as this: practical sources have decreasing terminal voltage with increasing load current. So think about it. We know that voltage drops are IR drops. So that means if you have a fixed amount of resistance, the higher the current, the higher the voltage drop. So because we have internal resistance in a practical source, every time we draw more current from that source, we're going to have more internal voltage drop. And once we have more internal voltage drop, that means there'll be less voltage available to the load, the work producing load that we're connecting, such as a lamp, a heater, a motor, and so on. So ideal sources have no internal resistance. An ideal source, the terminal voltage does not change when the load changes. For a practical source, there's internal resistance, so as the load current changes, the drop across the internal resistance changes and the terminal voltage changes. Okay? So what does that look like when we look at what we've covered so far? Well, if we look at the first example here, we can see we're talking about an ideal voltage source. It shows no internal resistance. It means that the terminal voltage, and this is important, this box is considered to be the source itself. There is where you have the terminal voltage. That's the plus and minus terminal of your car battery, or the plus and minus terminal of a battery you would connect to a flashlight or some other device. That's called the terminal voltage. When it comes to the practical DC source, we have the ideal part of it, which is the voltage value itself, and then we have the R internal, it's called, or the internal resistance of the source. This is the part of the source that drops voltage as the load draws more and more current. So let's take an example over here. Here we're comparing two practical sources, one with a low internal resistance of only 0.02 ohms, which would be 20 milliohms. And down here we have a significantly higher internal resistance of 100 ohms. In each case, we're talking about a load with the same amount of resistance. So that means each one of these loads is looking to draw the same current from this practical source. It's looking to draw the same current. But what we will see is because of the significant difference in the internal resistance here, the results of terminal voltage that we get is hugely different. We are going to have near 12 volts for this one because of its low internal resistance. We are going to have near 0 volts here because of its high internal resistance. So let's go to the textbook again, and we'll do some whiteboard work with this example and calculate some figures, and you'll see what I'm talking about. So here's where we see that ideal source versus a practical voltage source. So we would call this a practical source. So if you were asked what's the difference between an ideal source and a practical source includes internal resistance. You can see here in the ideal source, it doesn't matter what value of current I that's being drawn from this source, the terminal voltage will always be whatever the value of voltage is here. If it's 18 volts, then that would be 18 volts regardless of the current here. Potentially, current could even equal an infinite value and we'd still have 18 volts. We know that's not real. We don't have a source that's capable of doing that in real life. So for a practical source, we have to include the internal resistance. But I do want to point out, it doesn't matter whether you're talking about an ideal source or a practical source. The terminal voltage is the important term here, describing the voltage across the two terminals of the source. So when we have V terminal or terminal voltage, it's including the voltage drop of VR internal. So what would that mean then? Based on what you know about Kirchhoff's voltage law, which still applies here, it means that terminal voltage for a practical source will always equal E source minus V R internal. put another way, E source minus I total times R internal, because that describes an IR drop for a voltage. Okay, so here's where we look at that example. One of them is with a low internal resistance of 20 milliohms. The other is with 100 ohms. Both of these are 12 volt sources. But if we look at the same load of 100 milliohms or a 0.1 ohm, we can see down here the results of a VAB value, or what would be called V terminal, right? So this is determining our terminal voltage in each case. VAB is our terminal voltage. So based on VAB being our terminal voltage and what we see here, notice with the low internal resistance, this load is still going to be provided with 10 volts of source voltage. Notice in the last example with the large internal resistance, the source voltage is negligible. You wouldn't be able to even drive that load with a voltage such as this, as 12 millivolts of applied voltage. So this is the effect of internal resistance on practical sources. And so when we do questions involving practical sources and internal resistance, I'd say probably the biggest kind of suggestion I would give you, or a piece of advice I would give you, because this is often seems to be difficult for beginning students, is just remember that this is a circuit that is a series circuit like any other. So it means you have a R internal in series with an R load. RL means R load. And it means that whatever the value of ES is here, that's going to be the same value of voltage across here. This is where we're going to see ES voltage here as well. So it means you can subtract the load voltage from ES to get the voltage of R internal. You can subtract R internal voltage from ES to get R load. You can determine R total as R in plus R load. You can determine I total as E source divided by R internal plus R load. That's the biggest sort of mistake I see with beginning students, is they throw away sort of the concepts of a series circuit and the fact that current is the same throughout. Kirchhoff's voltage law applies. So the sum of the voltage rises equals the sum of the voltage drops, and so on. So I think if you just remember that, you'll do a lot better on these type of questions. So we'll conclude this presentation with this. Here we have a multi-sim simulation of a practical source. That is to say, a source that includes internal resistance. So if you look here inside the box, we have the ideal source with the source voltage of 18 volts, and we have in series internal resistance of half an ohm or 500 milliohms. I added an ammeter here inside the source just so you can see the source current. Now in this case we've got V terminal represented by a voltmeter between the positive and negative terminal of the source. If we looked at those previous drawings, V terminal was showing the terminal voltage between the two terminals of the practical source, the positive and negative terminal. So in this case, even though this looks like a parallel circuit, and if I was to close more than one switch, it would become a parallel circuit, but I want you to realize that with me just closing one of these switches at a time, this is our simple series circuit example. We have R internal in series with one of these loads, depending on which switch that I turn on. So look at how I have all of them open at the moment. With all of them open, this is representing our terminal voltage, or what is otherwise referred to as open circuit V terminal, no load voltage it's called, V terminal, open circuit. All of these examples or terms that I just used are describing what we see here. No load connected, no load current, and an open circuit V terminal. This is handy because this tells us what the internal voltage is with one measurement. If we didn't know this was 18 volts, an open circuit V terminal would allow us to determine what the internal voltage was, because we know without current we will have no voltage drop of our internal. So this open circuit value will always tell us what value the internal voltage is. Okay, so what happens if I close switch 1? I'll be connecting a 30 ohm load. Switch 2, a 15 ohm load. And lastly, switch 3, a 5 ohm load. We know that current and resistance have an inverse relationship, so notice how in each case I'll be dropping the resistance, and in turn I'll be increasing the current. So with each one of these loads I'll have a greater current than I had before. So let's look at now the V terminal voltage when I connect a 30 ohm load. So switch number 1 is closed now. And with switch number 1 closed, notice how we have a V terminal value of 17.705 volts. So that means we've essentially lost 0.3 volts of our source voltage. And how do we explain that? Well, now we have current. And from this current, we can see we have 0.6 amps of current. We take that 0.6 amps, we multiply it by half an ohm, and that gives us 0.3 volts. And that explains why we've got less terminal voltage with current than we did when we had no current. So what will be the case when we increase our current by dropping our resistance? We are going to have obviously a greater voltage drop from our internal and less terminal voltage. One way to describe a practical source is that it has decreasing terminal voltage with increasing load current. Notice we increased the load current here. What was the result? A decrease in the terminal voltage. And how is that explained? Because it's a practical source that includes internal resistance. Okay, lastly, let's look at the highest current load, the one with the least resistance here, and have a 5 ohm load. Notice how with the 5 ohm load, our load current, or our series circuit current, is 3.3 amps now, and as a result we've got a drop that's significant for the internal resistance, and our terminal voltage is 6.36 volts. Okay, if we open that again, now we're back to our open circuit V terminal value, indicating the value of the ideal source inside. So that's just an example to illustrate practical sources. But I would remind you, when you're doing any of your questions regarding this, remember the terminology like the V terminal value. Remember you're working with load terminal values when the load is connected, or open circuit values when the load is not connected. And open circuit values, V terminal will equal ideal source. And when you have load connected, V terminal will equal V load. Notice the difference. So hopefully that'll help you. Remember, you're just working with a simple series circuit where current is all the same and Kirchhoff's voltage law applies. Okay.